Good afternoon, everyone. Let's get started. My name is Sharon. I'm with BLT. I want to thank all of you for joining us today. In today's 30-minute webinar, we'll talk about cross-triggering, have a live demo, and then follow that up with a Q&A session. I did want to let everyone know that this webinar is being recorded, and we're going to hold all questions for the end during the Q&A session. So please use the chat panel on the side of your screen to ask questions as we're going through, and we'll get to them at the end of today's demo. Before we begin, please let me tell you a little bit about BLT. BLT provides custom electronic solutions for commercial and government IC aero applications. We design custom chips, embedded software, circuit boards, and complete systems. BLT trains 1,000 student days a year and works on dozens of board, FPGA, MPSoC, and ACAP projects as well. Some of our projects include work on the Mars rover, designing the prototype for HTDV, helping develop satellite radio, and implementing one of the earliest RFSec designs ever done. BLT is where projects come to life. We're a certified Xilinx Alliance member and also a Xilinx authorized training provider. Today's presenter is Ellie Rosen. Ellie is an engineering manager at BLT, primarily focused on ACAP, RFSoC, and MPSoC designs for both commercial and defense applications. In his prior roles, Ellie has specialized in custom ASICs, ARM-based processor applications, and is a general tech enthusiast that enjoys playing with SDRs and home automation on the weekends. Just like many of you here today, he has spent countless hours troubleshooting complex systems in simulation environments, as well as at the lab bench. Thank you, Ellie, for taking your time today to show us how to incorporate these techniques into our debugging tool belts.
All right, Sharon, thank you for that introduction. Today we're going to cover a few different topics, mostly revolving around using the cross-triggering methodology to debug hardware and software designs. We're going to take a look at how this operates under the hood and the mechanisms that allow this for us to be able to utilize these things on our embedded systems. And the majority of this webinar is actually going to be a live demo where I will create a Vivado design and very basic, has some AXI peripheral connections. We'll then load the Xilinx support archive into the Vitis software and actually do a debugging emulation in real time. And then at the end, we'll wrap it up with some questions. So oftentimes, if you're just a hardware engineer, you'll primarily be used to running simulation tools such as within Vivado, the X simulator. Many other vendors as well have their own simulators that you might be accustomed to. Then when we go to the bench and we want to make sure that all of our clock domains are correct and that we're not, that the things that we did in simulation actually match the real hardware, we'll take that logic to the bench and we'll put in things such as integrated logic analyzers and VIOs, virtual inputs and outputs. And that allows us to drive and see circuitry in real time on the hardware. On the software side of the coin, software engineers will use tools such as TCF and GDB to debug their software on the fly, be able to take a look at processor memory, registers and variables, and allow you to step through your code as it is operating. However, one little gap here is what do we do if there's a problem that exists somewhere between the hardware and the software, and we're not quite sure where that exists. In order to accommodate for this, and in order to make sure that we can fully resolve any issues that there might be in a design, this is where cross-triggering comes into play. Sometimes this may also be called hardware-software co-debugging. Under the hood, there's a basic handshaking mechanism that is used between the processing system of a Zinc device or a microblaze device that also talks to the integrated logic analyzer in the programmable logic. In the processing system side, we have a trigger import. That trigger import will respond back to the device that is providing that trigger with an acknowledgement, and then vice versa, there is a trigger output, and it will receive back a trigger out acknowledge. So that's something that would occur on the processing system side. On the hardware side, we have the exact opposite. And the end result here is that we're able to, in real time, have an integrated logic analyzer turned on. We can trigger just like how we normally trigger, but when we hit the trigger button, we could also freeze or set a breakpoint in our software. And then on the software side, we can have a breakpoint in software cause a trigger in the hardware so that the hardware will pause and do a capture at that moment. So today I'm going to show you guys how to do both ways, the software triggering the hardware and the hardware triggering the software. You don't necessarily have to always do it both ways. You might only want the software to trigger the hardware. It is up to you, but for purposes of this demonstration, I'm going to show you how to do all of it. So let's get into the demo. I'm going to start opening up, in this case, I'm using Vivado version 2020.2. This process works in any version of Vivado. I'm going to create a project. And for this design, I'm going to call it Cross Trigger Demo. And I'm going to put it in this folder on my C drive. I'm not going to specify any sources at this time. And I'm going to be demonstrating this on a ZCU 104 Zinc MPSoC evaluation board. Now, I do want to remind everyone, for the purposes of this lab or demonstration, I may go a little quickly. I do want to make sure that I can get across the points that are most important to the cross-trigger debug. If for some reason you do need to go back and reference this a later time, we will be sending out the recording of this webinar, and you'll be able to go through it at your own pace. Now that I have my empty Vivado project here, I'm going to create a block design. So I'm going to call this Cross Trigger BD. And then we'll get to our blank IP integrator canvas. So the first thing I'm going to do is I'm going to put down my zinc, because we're going to want to have the zinc trigger our hardware. All right. So here is my zinc IP. I'm going to double click it so that I can customize it. And we're going to want to turn on the triggering ports. And those triggering ports are underneath the PSPL configuration. So if I go to PSPL configuration and then to debug, I have the options here for my cross-trigger inputs and my cross-trigger outputs. And I'm going to turn one of these on for both the input and the output. All right. The next thing that I'm going to add here is the hardware that's going to be the device that we want to trigger on, or evaluate the data going through over an AXI interconnect to this peripheral. So for that, I'm going to use an AXI GPIO module. This GPIO module, because we are using a Xilinx evaluation board, I have the ability to make this GPIO module board aware. And so what that means is, if I specify here that I want this GPIO block to talk to the 4 bits of LEDs on my board, I just specify this here. And when I run the block automation, it'll automatically connect to those pins, and I won't have to specify the design constraints to make that happen. So I'm going to run some automation here. The first thing I'm going to do is apply some board presets. Because I'm using the evaluation board, I just want to make sure that my zinc configuration matches the configuration of the board. The other thing that I want to do here is connect the GPIO to the zinc. So for right now, I'm going to just connect the GPIO interface and the AXI interface to the zinc processor. All right, so what we're left here, I'm just going to clean this up. So what we have here is we have our zinc we have a AXI interconnect, we have a synchronous reset block, and we have our AXI GPIO that goes out to our 4-bit LEDs. All right, so now the signal that I want to look at is this AXI interface over here. So one way to do that is to use a system ILA. So I'm going to add in another piece of IP. And what this piece of IP allows us to do is to probe down and kind of squid cable on top of the signals here and be able to see them and trigger on them as data is flowing across them. So for this, I want to take a look at this AXI interface, so I'm going to click and drag to connect these signals. I also want to open this up, and I want to enable the trigger ports. So here I can specify that I want the ILA's trigger out ports turned on, and here I want the ILA's trigger in port turned on. All right, so now I get these trigger ports accessible. The last thing that I'm going to do here is run the connection automation. I'm going to take advantage of this to have Vivado automatically make the remaining connections that I need. So that way I make sure that all my clocks and resets are connected, as well as these trigger interfaces are connected appropriately. All right, so that made all those connections for me. All right. The very last thing I'm going to do here is make sure that I have an address specified for my block diagram. And then for every block diagram, before you generate it, you need to validate it. So this will run validation. It'll let me know if all of the interfaces that I've connected are okay, if there are any clock domain issues, any type of reset maybe that wasn't connected. This will let me know if that happened. In this case, validation was successful. What that means is I'll be able to generate the block design and create the HDL wrapper. All right. So for this particular design, and while that's updating, this will then be the top level for our design. For sake of time, normally what you would do here is you would go through the rest of the process in Vivado. You would first you would generate the block design, then you would synthesize it, implement it, generate the bitstream. For purposes of this demonstration, I've already done that to save us the couple or so minutes that this would take. So now what I'm going to do is switch over to the completed example that I have. All right, so here's my completed example. The only difference is that now the bitstream has been written. Once you complete your bitstream, and if you have an embedded Zinc design, you're going to want to export the hardware. This will create the Xilinx support archive that will be used inside of the Vitis integrated development environment for writing your code to go on top of the Zinc processor. So in this case, I would export the hardware to include the bitstream, and I would put it in the folder that this completed design exists in, and then it would put that file there. For the purpose of this example, I'm not going to do it in this case because then I'd have to recompile all of my code, but this is the steps that you would follow. All right. So the next thing I want to show is my hardware. So sitting next to me, and I'm going to switch my camera, I have a ZCU 104 evaluation board. So this evaluation board has a 7U EV part that it contains the video codec engines. It has a slot for external DDR memory, a slot for M.2 memory, HDMI ports, a display port, Ethernet ports, some PMOD, as well as a FMC expansion header. For this demo, we're going to be looking at the push buttons here. And on top of each push button, there's a single LED. So we're going to be turning on those LEDs. We will be stopping and pausing them and showing how the triggering works with those LEDs. The other thing that I want to show, if you take a look back at my screen, is I'm going to connect to this hardware. So when I connect to this hardware, the first thing that I'm going to notice is that there's no bitstream program because I just turned it on. All right, so I've connected to the hardware server on my PC. The device is not programmed, so let me program that for you guys. All right, so I am programming that bitstream along with the debug probes file that was generated when I created the bitstream. And I want you guys to pay attention to what happens here because this is something that many engineers run into. Nothing came up. And the reason for that is if I look down in my console here, the debug core hub core was not detected. That is because there are no clocks running. If you recall back to my completed design here, the clock that I use for this design is comes generated from the Zinc. But in this case, I've only just turned on the board in JTAG mode, and I have not loaded any software, which means this clock is not being generated, which explains why I get that warning message. So let's fix that. If I go to Tools in my completed design, I can launch the Vitis IDE directly from here. All right, so the Vitis IDE is launching. I'm going to show you the workspace that I already have. So in this workspace, I have a hardware platform, which is the XSA that has come from my Vivado project. And I also have a cross-trigger app. Now what this app does is this is going to run on the hardware. And in my main function, I'm going to initialize a AXI GPIO driver. I'm going to set the direction of those pins. 0 are for outputs, 1 would be for inputs. I'm going to then set all the LEDs to be off. And then I'm going to go into a while loop that I can never leave. In this while loop, I'm going to count up to the value 16. And then every value that gets, every iteration of the loop will increment the LEDs that are turned on the board. And then I have a few conditions that we're going to take advantage of for the cross-triggering. Here, if the count is a remainder of 6, then it will print out the count message. Otherwise, if the count is equal to A or 10, it'll print out a different message. So before I begin, let me connect my serial console. Sorry, serial terminal. All right, and I'm going to connect this to the hardware. All right. So in order to demonstrate the hardware debugging, we're going to want to use a special debug configuration. If I go in and create a new debug configuration, a window will pop up. And if I go to the target setup, I specify the series of instructions that Vitis is going to follow to load my software onto the hardware. So the very first thing that I'm going to do is reset the entire system. I'm then going to program the FPGA with the bitstream that I included inside of the XSA. And then I'm going to initialize using a first stage bootloader. What that's going to do is it's going to turn on the clocks and disable the resets within the programmable logic. Now this field here, the enable cross triggering, This was only added here because my hardware description file includes that there is a cross-triggering port. If you have a design that does not have cross-triggering enabled, you will not see this here. Now for my cross-triggering, I want to turn a few settings on that can enable breakpoints. So if I take a look here, let me just close some of these to make it easier to see. There are 4 ports that we want to turn on. So the first one is the input side for the cross trigger. On the A53, we're going to turn on or enable this debug trigger port. On the acknowledge side, we're going to turn on this fabric trace module system trace macro cell connection, FTM0. Then for the output, this will, if I hit a breakpoint, send out a signal over the external debug requests interface. And then it will also, on the FTM0, be able to receive that acknowledgement coming back. All right, so with those specified, I will now be able to cross-trigger on my software. All right, so I'm going to now take this and I'm going to program it to my ZCU 104. All right, so it's programming the FPGA. All right, it ran the first stage bootloader. And because I'm in debug mode, it automatically sets a breakpoint right at the beginning. I could have disabled that in my debug config. But now I'm going to tell it to resume. And now it is running. So what we see here is the count is incrementing. And if you look, let me disable that breakpoint. And this will continue to run forever. And if you take a look, the LEDs are counting up in a binary pattern. All right. So I can set a breakpoint where if I get to this message by double clicking here, the next time it comes around to that message printing out, it will halt, which is what's happened here. Let me turn that off. All right. So if we go back now to our hardware manager, we can now refresh the device and it should be programmed. Also, the probe signals have now appeared because our clock is running. So here I have my AXI-Lite interface. I have the address read channel. I have the read data channel. I have the address write channel, the write data channel, and the B response channel. So what I can do here is I can just run an immediate capture. I want to see what's on the bus at this time. And it triggered. And let me just close these to make it a little bit easier to see. And in my 1024 samples of capture, I have no active data. And the reason for that is because I believe software is currently paused. If we have it continue running, so now we see the LEDs blinking again, and I try to capture again, well, once again, same thing. I don't actually see any data because the software is running so comparatively slow to how fast the hardware is running, I'm not able to catch that happening. So this is where triggering comes into play. If I turn on a trigger probe where I say, if I'm writing data, if data is valid, so I want to just trigger the next time data is valid. So I'm going to say if data valid is a 1, let me trigger. So this will now arm that. And we caught it. If I look in the right channel, I can see that for this one clock period, we were the value 1, and I caught that data there on that one sample. All right. I also want to add here the right data. What if I want to trigger on, for example, the value A? So if I look at the data interface, I could say don't trigger until I see the value A. So if I do this here, this is going to take a lot longer to do that capture because I have to wait all the way until my count gets to the value 10. And it happened, and I see my trigger and my data is A. So right now, all we've looked at is the software just continually running, and then the hardware's triggering. So now, if we want to have the software trigger hardware, what we would do is we would change the trigger mode here. And instead of being set to basic, we will set it to trigger in only, which means this ILA will only listen if the trigger in input is toggled. All right, so I'm setting it to trigger in only. I'm going to set this sitting here. At this point, it should be ignoring my trigger setup over here because I'm only listening to the trigger import. And if I go back to my software and I set a breakpoint, for example there, my breakpoint was hit and my software halted. So I did a capture. But if we look here, I can't actually see the transaction. And the reason for that is because from the time software sent out its breakpoint command to the time this trigger was triggered, we missed it. One thing that we could try doing is moving the position of our trigger point. So if we move the position of our trigger point, let's say to sample 1, we can try this again. So if I arm it and then continue it, the next time it comes around to that point, our hardware will get triggered, and in this case, we were able to capture it over here. All right, so there is now that trigger where the software breakpoint triggered the hardware. All right, so let me go back and let's turn off the breakpoint here. And the next thing that we want to do is have software continuously run. So that's what I have now. Software is continuously running, and I want an event in hardware to cause the software to stop. So what I'm going to do now is I'm going to say, I want to stop when I get the value B. All right. And before I trigger, we can set this to basic or trig in, or just basic in this case. And then in our trigger out mode, we're going to set it to trigger only. The other options here, trigger in only means that if I get a trigger in, it'll just pass it out, which means you can daisy chain a bunch of these trigger mechanisms, or you could specify this, which will just OR the trigger in with the trigger. But for this case, this example, I'm going to just trigger on this in my ILA. And when we hit the value B, I should get a trigger. And as you see, what popped up is Vitus, because I hit my trigger B. I see my data here is B, and in Vitus, I stopped as soon as I received it there. So there's a lot of different ways that you can take advantage of this capability. This is just one example. There are a few classes that we offer that go through some of the practices and methodologies for doing more than just this trigger, capture, and debug. And I hope this was informational for you. Before we get into some questions, I believe Sharon has some information she'd like to share with you all.
Thanks, Ellie, for taking time to demonstrate cross-triggering for us. Everyone watching live, if you have questions, please go ahead and put them in the chat panel to the right of your screen. I see we already have some. Before we get to those questions, I just want to remind everyone that this webinar is being recorded, and we'll send out the recording via email when it's ready. If you like today's webinar, I also wanted to let you know that we have a debugging course called Advanced Debug Techniques for Hardware Engineers, and that's coming up on January 18th of 2022. I know that feels like it's really far away, but it's not. It's a one-day class, and in case you were curious, it's $2.99, which is our standard daily rate. Ellie will be teaching that as well. We also have our Embedded Systems Hardware Design Bootcamp for the Zynq UltraScale Plus MP SoC, which starts on December 9th. That's a 3-day course. And I'll drop the links in the chat panel to the course descriptions for both of these classes for you. Also, our next featured webinar is in January, and that's going to be using incremental compile flow to save on place route time. Make sure to sign up for our newsletter to stay up to date on all of our learning opportunities, and I'll drop the link into the chat panel for the webinar as well. Okay, Ellie, I believe we have a couple of questions, so let's go ahead and get started on the Q&A.
All right. So the first question that we have is, will this approach work with an operating system as well? And if I understand your question there, is the intent that if you wanted to debug, for example, like Peta Linux with the hardware, that is something that TCF and GDB do support. So if that answers your question, I think that might be what you're looking for there. Another question that we have is, does the cross-triggering work in the same way with the SDK? And yes, it does work in exactly the same way. Where that cross-triggering icon is a little bit different, but the premise is still the same. Also for the Zynq 7000 series, the ports aren't named exactly the same as they are in the A53, and information on that could be found in the Zynq 7000 technical reference manual. We do also have a question on if there are example sources provided, bd.tcl in the C file. If you're interested in that, you can send us an email to info@bltinc.com, and we can try and get that for you. Or you could also recreate from the video the steps I just followed. You also asked how high a compiler optimization level can these techniques be used at? And O2 or just O0, that is not something I've personally experimented with, but I'd encourage you to turn that on and see if that has an impact. Generally, this is done, just in the debug perspective. So, usually in your production or your run configurations is where you would turn those optimizations levels higher. So usually it's just O0 for the debug, and it could be worth the experiment for the O2, but I'm not 100% sure. There was a question earlier about the whether or not this could be done with the Zynq 7000 series, and so yes, this can be done on a Zynq 7000 series, as well as another question on can you use this technique to debug during an interrupt service routine? And yes, you can use this during an interrupt service routine. Same thing with setting breakpoints. You should be able to accomplish the same thing here. Martin, that's a very good question on debugging a real-time O2 system. And for that, I would definitely encourage you to send an email to info@bltinc.com. And that definitely sounds like a conversation that would be better had outside of this webinar. Does anyone else have any questions?
All right, everyone, last call for questions. All right, thanks so much for joining us today. Thanks, Ellie, for taking the time to demonstrate cross-triggering for us. If you like this webinar and want to join us for additional webinars, please use the links in the chat panel, which I will drop in right now. And you can sign up on our webinar on our website to hear more about our webinar series and training opportunities. That's bltinc.com. Again, thank you everyone for joining us.